A 58 kilogram mass must remain at rest along a 48-degree inclined plane. The coefficient of static friction is 0.14. The coefficient of kinetic friction is 0.08. Let me just interrupt right here and say, who cares about the coefficient of kinetic friction? Because we want this mass to remain at rest. So obviously the coefficient of kinetic friction is extra information that we don't need. What applied horizontal force is required to keep the mass in place? What's the minimum horizontal force that we need to keep this mass from sliding down the plane? So let's draw a free body diagram. There's our 58 kilogram mass. That 58 kilogram mass has a weight. That weight vector would act straight downward and would be equal to 58 times 9.81. But we want to break that weight into a perpendicular and a parallel component. The perpendicular component will be equal to mg cosine theta, which is 58 times 9.81 times the cosine of 48. The parallel component will be 58 times 9.81 times the sine of 48. We also have a normal force, which is always at right angles to the surface. We'll have a static friction force. The maximum static friction force is equal to the coefficient of static friction times the normal force. And we want to max out the static friction force here because we want the minimum applied force that we need to keep this mass at rest. And to achieve a minimum applied force, we need to max out this static friction force. Now unfortunately that applied force is horizontal, and it too is neither parallel nor perpendicular to the surface. So what we need to do is we need to resolve that applied force into components also. Now here's how we're going to do it. If we look at this top diagram, we can see this angle is 48 degrees. Now this dashed horizontal line, it's going to move down into the free body diagram. Watch this. Right there. Which means that this angle right there is 48 degrees. And if this dashed line represents FA, then hopefully you can see that this green vector would be FA times the cosine of 48. And this black vector would be FA times the sine of 48. Now we're ready to start writing Newton's second law equations. Let's do the perpendicular direction first, as always. If I choose Fn to be in the positive sense, then 380.72 is in the negative sense, as is Fa times the sine of 48. The sum of those forces by Newton's second law should equal the mass of the object times the acceleration perpendicular to the surface. The acceleration perpendicular to the surface is 0, which means the right side of this equation will reduce to 0. Now we can't really solve anything in this equation yet because there are two unknowns in it. So let's write the other Newton's second law equation, the one for the parallel direction. If I choose down the plane to be positive, then 422.83 is positive. 0.14 times the normal force is negative, as is Fa cosine 48. The sum of those forces should equal the mass of the object times the acceleration parallel to the surface. We want the mass to remain at rest, so again the right side reduces to 0. Here again we have two unknowns in this equation as well. So what we have here is what's called a system of equations, where we have two equations that are independent of each other and two unknowns. There are any number of ways that you might solve this, but the way that I'm going to walk you through is to solve one of the equations for one of the variables and then plug that in to the other equation. So I'm going to call the top equation single asterisk and the bottom equation double asterisk, and as you can see what I'm going to do here is solve the first equation for Fn. That's what we'd have there. The 380.72 would appear on the other side of the equation as positive, as would the Fa sine 48. And then, right there where Fn is, instead of putting Fn into the second equation, I'm going to put this whole thing, and I'm going to stuff it in there. And we're going to do that on the next slide. So there you have it. Right there, that's equal to Fn from our first equation. And now it's just a question of doing the algebra correctly and solving for this applied force. Yeah, I know, but it can be done. So there's our 422.83. If I take that, that's going to reduce to 0.104 FA. Remember that the sign of 48 is just a decimal. You can type that into your calculator. So you're going to go sine of 48 times negative 0.14 times FA. That's what this comes out to be. Now we're going to distribute the 0.14 with the 380.72, and that will lead you to negative 53.30. Remember, there's a negative sign in front of that 0.14. Similarly, I'm going to find the decimal form of cosine 48, which must be 0.669. That whole thing should equal 0. So now we're going to combine like terms. I've got two terms with the applied force and two constant terms. I'm going to put the constant terms on the left side of the equation, put the applied force terms on the right side of the equation, divide by 0.773. The applied force turns out to be 480 newtons.